We've introduced the term extensive to refer to a reaction that ends up mostly products at equilibrium. We related this to the value of the standard free energy change, delta G0. But there's another way to quantify equilibria that's sometimes easier to work with, and that is called the equilibrium constant. The equilibrium constant is given the symbol capital K. Conceptually, K gives the product-to-reactant ratio when a system reaches equilibrium. We can think of it as the amount of products over the amount of reactants. The actual mathematical form of that ratio is somewhat more complicated. We would call that mathematical form an expression for K. In general, the expression for K is this. The capital Pi's in the expression indicate the product of, or multiplying together. That is, of course, different than if you saw a capital sigma, which would indicate the sum of or addition. Here it is multiplication. The square brackets represent concentration of. In the numerator, it is the concentration of each product in the balanced equation raised to a power that is the coefficient of that chemical species in the balanced equation. In the denominator, we have the concentration of each reactant raised to its coefficient in the balanced equation, all multiplied together. This is the expression we will use for the equilibrium constant. Technically, we should be using what is called the activity of each reactant and product. The activity is a measure of how far away the amount of a material is from its standard state. For solutions, this is numerically equal to the concentration. For gases, we could use partial pressures, but pressures are proportional to concentration. Try proving that to yourself using PV equals nRT. So we will use concentrations for gases in this course. For solids and liquids, they are in their standard states if they are present, so their activities are 1. So concentrations of solids and liquids do not appear in expressions for equilibrium constants. We need to become adept at writing expressions for K, so let's do a few examples. The first says, this reaction is in solution. CH3I plus OH1 minus goes to form I1 minus plus CH3OH. Since everything is in solution, we'll use concentrations. Also note that the coefficients are 1 for all of the chemical species. So in this case, all of the concentrations will be to the first power. For the expression for K, in the numerator we have the concentration of iodide ion to the first power times the concentration of methanol, CH3OH. These are the concentrations of the products, each raised to the first power and multiplied together. In the denominator, we have the concentration of CH3I to the first power times the concentration of hydroxide to the first power. This would be the expression for K for this reaction. In this reaction, dinitrogen gas and dioxygen gas form 2 moles of nitrogen monoxide gas. Though using pressures is valid for a gas phase reaction, we will use concentrations here. In the numerator, we have the concentration of the product, NO, but notice it is raised to the second power. In the denominator, we have the concentrations of the reactants, N2 and O2, each raised to the first power and multiplied together. Notice that the powers of each concentration come from the coefficients in the balanced equation. Our third example has solid lead-2 chloride forming lead 2+ ions and chloride ions. Notice that it is important to have the states of matter in the balanced equations. In the expression for K, we have the concentrations of the products. Notice that the chloride ion concentration is raised to the second power due to the coefficient of 2 in the balanced equation. Why is there no denominator? Well, actually it's there, but since solids appear in the expression as 1, we don't need to include it. It won't change the value of K. If we have data for the concentration of reactants and products at equilibrium, we can evaluate K. The challenge is to first write an expression for K. Then we simply plug in the numbers. For this reaction, we're given the concentrations of N2, O2, and NO at equilibrium, and we're asked to evaluate K. First, we need an expression for K. We derived that a couple of moments ago with NO squared in the numerator and N2 and O2 in the denominator. Once we have the expression, now we simply plug in the numbers. The value of K is 1.9 times 10 to the minus 4. Here is a problem where we are again given a reaction and given concentrations at equilibrium. Again, we need to start with an expression for K. We derived this previously. Plugging in the equilibrium concentrations gives us a value of K of 6.9 times 10 to the minus 9.